Hello, my name is Mark Miquelon. I'm Director of Partner Alliances in Western Digital's Platforms Division, and today I'm going to talk to you about open composable disaggregated infrastructure. 5 main points we're going to cover today. What challenges are solved with an open composable disaggregated infrastructure? How does open composable disaggregated infrastructure really work? Who is enabling the open composable disaggregated infrastructure ecosystem? And what are some examples of organizations that have benefited from the open composable disaggregated infrastructure? And I'll close with an introduction to a lab that we've created called the Open Composable Compatibility Lab. First, a little discussion on what's driving this. So we're all seeing a huge change compared to prior years in terms of how much data we're being hit with in our data centers. So there's a volume, there's a velocity, there's a variety, and there's a value to this data that are all very different today than they were just a year or two ago even. Different applications, different workloads, different service level agreements are required to service these applications and workloads. And there's a combination of what we call big data, so large data sets, things that scale and you want to run analytics on, and then fast data, things where making a decision on a piece of data in real time is critical. These things all drive different use cases and different workloads inside the data center. And to some degree, they're all competing for the same hardware resource. And so how does your design of your data center respond to that? Another thing that we're all dealing with is the cloud. And we've seen a lot of people move data to the cloud. Some people are happy and are putting more data in the cloud. Other people have tried that and they're now bringing back to their on-premise data center. In general, though, what we're seeing with large organizations is everybody has a mix. So you're using some on-premise, some cloud, and that's a factor that we have to deal with as well. For the on-premise version of that, this change, right? Change in the velocity, change in the variety, change in the volume and value of the data needs to be dealt with. And the most common way we see people dealing with that is over provisioning. And what I mean by that is that there's some amount of compute or storage or both in your data center that's there waiting for the peak demand to come. And so it's not being used today, it's not giving you value today, but it's a little bit like an insurance policy, right? It's there when you need it and you can turn it on as needed. And everybody has this to a different degree. We've seen underutilization approaching 45% in both storage and compute capacity, which is expensive. It is a good security blanket, but it's expensive. And so one of the things that an open composable disaggregated infrastructure can do for you is to let you better utilize the resources you have and be able to more quickly bring new ones online if needed. So what does this really look like? On the left in this diagram, we're representing a typical server with the blue box. And so inside that server, you're going to have a CPU, memory, direct attached, and then across the PCI bus, you're going to have a storage, a NIC, an Ethernet attachment for sure. You'll probably have some storage, flash or disk or both. And you may or may not have other accelerators, either Fpga or GPU. Many data centers will qualify servers in a fixed configuration, and they may have multiple, right? They have some small number of servers that have been qualified to do specific applications. And when need comes up to either expand capacity on those applications or to add a new application, people will pick the server that best fits the need, and they'll order more of those servers, they'll rack them up, they'll bring them online, and they'll start running that application on that new server. And so we call that scaling by adding servers. It's very common, and also it's inefficient. And the reason is that not all applications drive the same workload or have the same demand, and you can't really qualify an infinite number of server configurations either. So there's a trade-off there. And so what we see is somebody may have an application that's already running. It needs more memory. Okay, it's memory bound. So what will they do? Well, they'll add servers that have more memory in them. And in those servers, you're probably getting some flash or disk, you're getting Ethernet attached, you're getting more CPUs in addition to the memory, and you may not need all of that. And so that's where the inefficiency comes in, is you're buying hardware resources that you don't need. So what we've proposed is a composable disaggregated infrastructure on the right. And we changed the sheet metal. So you can see that there's no big blue box around any of this, that each resource has its own sheet metal. And those resources are connected to each other over a fabric. The fabric could be PCI if the scale of this implementation is fairly small. But what's more common and more useful actually is a fabric that scales better, like Ethernet. And so as long as you can connect these hardware resources using the fabric and then compose virtual systems, or orchestrate is another word for it, virtual systems out of the resources, this brings a lot of flexibility. So if you need more CPU, you can just scale up the CPU. It will come with memory at this point, but in the future, when memory technology better lends itself to disaggregation, you can disaggregate the memory as well. If you just need more flash, you can scale that. If you just need more GPUs, you can scale that. And so we call this scaling by adding devices. And so it is more efficient in that sense. You're never having to add something that you don't actually need. It does require the fabric interface to be able to do that. So what does this really look like? So in this example, you see across the top, we have the same hardware resources. Implicit in this is a fabric. So these things are all connected to each other over a fabric. And now I introduce a piece of software or a DevOps person that wants to orchestrate virtual systems. And so in virtual system number one, we have a CPU, we have a GPU, we have some flash, and we have some memory. And you can see that we've blocked out those resources in the available pool at the top because now they're committed. They're committed to this virtual system. We want to add another one. We have more resource available, so we go find 2 more CPU cores. We find some Fpga in this case, flash and disk and memory. And we carve that out and create a virtual system. Similar to number 3, this one is disk intensive and CPU intensive, doesn't really require much memory. And I'll show a 4th one here. In this, the 4th one is a little bit interesting in that there's no CPU required. So this might be a case where a data filter, for example, could be implemented as a computational storage element. You have an Fpga doing that computational storage. You have some memory for short-term storage of intermediate results, and then you're using flash to get your data and store your result. So the orchestration layer has gone out, discovered all these resources available, and then allowed us to create these 4 composite virtual systems with the available resource. They can be maintained for a short period of time, minutes or seconds. They can be maintained for a long period of time. All of our business have a different sort of cycle to them. Might be seasonal, might be daily, might be hourly. And that's one efficiency that you gain by going to a composable disaggregated infrastructure, is you're able to use your resources the way that cycle demands, because you can quickly create these composite systems, use them, and then return the resources to the pool. So I want to give some examples of what's actually out there and what's happening in this space. So for CPU, what's very common is to use servers you already have. Those are completely viable and usable in this architecture. What I'm showing here is something that's new, and this has been standardized in Open Compute. There's a project within the telco portion of Open Compute called Open Edge, and they literally have taken CPU and memory and 1 expansion slot and defined compute module around that. These are a good match for the open composable disaggregated infrastructure, and given the web link to them here, and there's at least 2 companies selling these today. So you can go out and buy these compute platforms today. On the GPU side, one example we're showing here is NVIDIA. They have a compute chassis that holds a lot of GPU resource, and it's also connected to Ethernet fabric. And you can actually go out and discover that GPU resource over the fabric and then compose that into your virtual systems like we outlined on the prior slide. On the FPGA front, this is not a product. This is more of a proof of concept effort that we've partnered with Xilinx on. We're working on it in our lab, but essentially it takes an FPGA device and the form factor that we've standardized in our F3200 flash device and combine the two. And we're looking at ways of creating a computational storage device that has flash and this FPGA available on the fabric. Not a product today, but if the proof of concept continues to go well, something that you could see productized from us in the future. Memory is the one resource that I would say is maybe a little bit ahead of its time in terms of being available for disaggregation at this point. There are a couple of standards that are pursuing this. Compute Express Link is one, and OmniExtend is another. I'm not exactly sure how all this is going to play out in the market just yet. What's important to know is that the architecture that we've developed comprehends disaggregated memory. And as that becomes viable, it'll plug right in. Flash device, I'll show you a little bit more about this coming up, but we have the F3200. We also have one called Data 24. I'll show you what's different about those two coming up on a couple slides, but the summary is they are fabric attached flash device that you can use in these composed virtual systems. Disk is something that we're studying as well. We have this on our roadmap. We will be using NVMe over Fabric to disaggregate disk the same way that we've done it with flash. So what does the ecosystem look like? So this is just another view of it. I've shown our partners here. So on the Fabric, I'll start with the bottom. On the Fabric, we've worked with Mellanox, Arista, and Broadcom to ensure that there's a plethora of Fabric, both from the switch perspective and NIC perspective. I talked about, for CPUs, the Open Edge project within Open Compute. And I've talked about our relationship with Xilinx and the POC that we're doing there. Ididicom is another vendor in this space. They have a slightly different way of providing computational storage, and that is also compatible with our F3200. Again, just some proof of concept stuff going on there. No real products yet. Memory is a future item, as I mentioned. And then flash is available today, and disk is available on Western Digital's roadmap. And then across the top, I show the orchestration layer. And so these are some of the partners that we've been working with. They have all consumed this Open Composable API, which is something that Western Digital contributed to Open Compute. And they've been able to pull these flash resources from Western Digital into their orchestration software and provide very compelling solutions to create virtual systems. This is a different device. We've announced this one and are just starting to ship it. It's called the Data 24. This is a more traditional looking all-flash array. So this has 24 SSD slots in the front and 600 gig Ethernet ports in the back. Again, runs NVMe over Fabric and uses the same orchestration interface that we've talked about that has been picked up by our partners. Okay, I want to give some examples of how orchestration really comes into play. And the first one is not really open. So it's not an open composable disaggregated infrastructure, but it is a composable disaggregated infrastructure. And this is what the major cloud service providers are doing for you already. So this would be people, Amazon Web Services, Microsoft, Google, etc. When you ask for resource from them, they don't go in the data center and set up a new machine, right? They have the resources in there. They have a software mechanism for carving up exactly what you've asked for and delivering it to you in a secure manner. And so that is composing a disaggregated system. What we've been talking about today is how you can do a similar thing in your own data center using the open composable disaggregated infrastructure. Second example here is one of our customers on the F3200. This is the ICM Brain and Spine Institute. Quite honestly, they haven't even really started using the composability portion of it yet, but they're very sold on the disaggregation. And so they had an example where they had new microscopes. These microscopes were studying brain issues in patients, And these microscopes, they had to actually dial back the resolution of the images they were capturing because their storage infrastructure could not store it fast enough. On top of that, once they did store an image in a workstation, they had to figure out how to get that huge file or that huge image to the place where the researchers were actually going to analyze it. And so with F3200, they sort of replaced that workstation with just a fabric connection. The storage is on the fabric, it's in another part of the building, but they gained two things. They're able to use the full resolution on the microscopes, offload the image very quickly, and then it's available on the fabric to any researcher anywhere in the building that needs to get access to it. And then the bottom picture here is provided by one of our partners, Liquid, who does the orchestration software. They have a customer who had two different use cases for GPUs, and we're contemplating buying a lot of GPUs so that they could do both artificial intelligence-based analytics during the day and video rendering at night. But with an orchestrated system, they were able to share those GPUs and use them one way during the day and a different way at night, and essentially save the hardware cost of buying double the amount of GPUs that they would otherwise need to get. Okay, another example here. So this is a customer that was using a distributed file system. In this case, it's BGFS. And they had a predefined storage server. You see it here. It's a 1U device, holds 12 drives. And as they needed capacity, they would put more servers online. We talked to them about their workload and what they were doing and discovered that F3200 was actually a good fit for this. And so instead of adding servers to gain capacity, they've been able to add F3200s to gain capacity. And they've been able to save themselves the cost of the CPUs and the DRAM and all the infrastructure that goes along with having those servers. And so they're better able to scale their capacity in this distributed file system. All right, and then I just want to wrap up with a piece on interoperability. So one thing that we realize is as you look at getting these resources from different vendors, right, and putting together the system that meets your needs the best, you want to have confidence that all these things connected to the fabric speak the same language, interoperate well, play together nice. And so we've created a open composable compatibility lab along with Broadcom, Mellanox, and Cumulus Networks. This is a place where a couple different compatibility tests can happen. So anybody that's creating a fabric attached device, so this could be a compute thing, a FPGA based thing, GPIOs, or other storage things, are welcome to bring this fabric device into the lab and go through some pretty rigorous testing on nvme-of fabric and the various Ethernet congestion management tuning and protocols that are available. So we have a very robust test suite that looks at all that. It's leveraged off of what's in place at University of New Hampshire's interoperability lab. So we're not repeating that. We're sort of taking the next step beyond what's tested at UNH. And then the other thing we have is the ability to check coherence to this open composable API standard that we've contributed to Open Compute. So if you have software that is using the API, or if you have a hardware device that is implementing the API as an orchestration control point, we can confirm your adherence to the standard on that. And so all this is intended to prove out interoperability issues before we're all in front of a customer. And so by the time we're doing this at a customer, everything works. And there's a lot of information available on what we mean by a lossless Ethernet network that's fundamental to making nvme-of fabrics work and work well. And all this is available at www.opencomposable.com. So that concludes my presentation today.